observe magnetic braking. The goal of this lab is to collect some observational data of a magnet falling through a conductive tube of aluminum foil. We'll model this magnet tube interaction using GlowScript, and then we'll compare the computational predictions with observed data. Just to preview the findings, we find the average time for the magnet to fall through the tube is around 0.73 seconds. If we use a magnetic dipole of a 1.4875 ampere meters squared, then the predicted time for the magnet will be 0.784 seconds. But if we adjust that dipole to around 1.43 ampere times meter squared, then the predicted time will match the observed time within a couple thousandths of a second. We are getting the original magnetic dipole from Lab 3. Key concepts: one is Faraday's law, which states the sum of the electric field over some contour to equal the negative change in magnetic flux. The flux is equal to the dot product between the magnetic field and the area where the field flows through. In this lab, we use the first equation for the change in flux. The electric field produced by a change in flux will be in the same direction as the current. Another key concept is magnetic force, which is just equal to the cross product of the current times the length vector with the magnetic field. And if you apply the current geometry as a loop, then you get this equation as above. Newton's third law states that equal and opposite forces, in this case magnetic forces on a loop, equal the magnetic force on the magnet. And Ohm's law says the current related to potential difference divided by resistance, and the potential difference is EMF induced, which is negative change in magnetic flux. Visual model: on the left you have a picture from the actual experiment. The system is the magnet and the surroundings of the tube and the earth. If we'll assume there's no air resistance from the environment. So basic flow of what happens is gravity will act, creating a downward force. The flux will change throughout the tube. Faraday's law says that this induces an EMF in the tube. Lenz's law says that those currents generate magnetic fields themselves, which exert an opposite force against gravity, but it won't be bigger than gravity, so it'll just slow down the magnet. The procedure is we'll use an iPhone app magnetometer from a couple of labs ago to mark the north pole of the magnet. We'll measure the following constants: radius and length of tube, the width of the foil, and the mass of the magnet. We'll be dropping the magnet through a foil tube 5 times, recording the time from the magnet entering and then exiting the tube. We'll model this interaction using code and GlowScript, and then we'll compare those results with the experiment. So here are the results. The average time interval is around 0.73 seconds, and then we've noted the measurements for all the constants and the times for all the drops. You'll notice here we input our constants, and we also do that here. This was from a couple of slides ago. Here's the dipole equation from Lab 3, and this is the change in magnetic flux over a certain amount of time equation. And then you'll notice basically we'll calculate it per ring. We'll calculate the magnetic force on the ring, and we'll add that up for all rings that make up the tube. If we can visualize the tube as a bunch of like continuous rings, then this ends up working. We set F net equal to the gravity plus magnetic force, and we plot it as such. So here in the red, you'll notice the magnet, or the red and the blue is the magnet falling. And then I believe it'll come with the time around 0.732 seconds. Dipole moment from previous labs, we'll note the simulation predicts 0.784 seconds. If we create a new dipole moment, just by decreasing it a little bit, it'll predict the magnet to take around 0.732 seconds to pass through the tube. Thus, it seems the lab might be inaccurate, and another dipole moment creates a more accurate time for magnet passing through the tube. However, we should note that this is just a marginal difference. It's not that big. Sources of error: there could have been contact between the magnet and the tube. If the magnet makes contact with the tube, there's friction force, which will increase the time artificially. There is air resistance, timing errors, and measuring with the meter stick. Smaller measurements like radius and thickness of the foil might be off. So the what ifs: what if the resistivity of the conductor were reduced to 0 almost? It would cause near zero resistance based on Ohm's law. Larger current equals larger this near zero resistance equals massive current because they're inversely proportional. Larger current equals larger force on the magnet, which means the magnet falls with far more time and lesser speed. What if holes in slots were cut into the tube? If there are holes in slots, then current can't flow, which means magnetic force goes down, which means magnetic falls with far less time and greater speed.